Okay, the diagram below shows the magnetic compass placed between unlike magnet poles. The north pole of the compass needle will point toward blank. Well, what you need to know is that if you have a compass and you have north and you have south, right, you always go from north to south, out of the north into the south. So in this case, the north pole of the magnet, actually, we don't even need to know about this for this one. We just want to know the north pole of the magnet. So, actually, the north pole of the compass. So your compass is in the middle of the screen, or in the middle of the page, rather. And the north pole of that magnet is going to be pulled toward the south, right? North and south attract each other. So if the south is over here, and this is the north pole, right? North and south, they attract each other. So it's going to be pointing towards C. Okay, next one. It says the diagram below represents an electric circuit. The equivalent resistance of this circuit is blank. So when you're finding the equivalent resistance, there's two ways to approach it, right? You have two formulas for this. If we look at our reference table, if we go to the electricity section, right, all about equivalent resistance, we have Req. If you forget, right, remember they tell you right here, Req is the equivalent resistance. You have Req equals R1 plus R2 plus R3, blah, blah, blah. Or 1 over Req equals 1 over R1 plus 1 over R2 plus 1 over R3 and all of that. So the difference is if you're doing a series or parallel circuit. So you need to know the difference, right? In a series circuit, you have only one possible pathway for that electricity to flow. We can only go around, for example, like this. But with a parallel circuit, there's multiple pathways for that electricity to flow, right? It branches out in different directions. This should be like one straight line, but I kind of messed it up. But you get the idea, right? The current can come around here, and once it gets to this point, the electricity can either go this way, or it can go down and around. So that's a parallel circuit, multiple pathways. If we look at the one that we have in the question, right, we have a parallel circuit. The electricity can go around in multiple directions. So what we have to do is use the parallel version. 1 over the equivalent is equal to 1 over resistor 1, or resistance 1, which we'll say is 3 ohms, plus 1 over resistance 2, 6 ohms, plus 1 over resistor 3, 9 ohms. If we want to add these, you could do it in your calculator just as it is, but I think it's a little bit easier if you just find the least common denominator and just add them up like that. So in this case, we have 3 over 9 plus 2, wait, no, that's not the least common denominator. Least common denominator would be 18, right? Because 9, 6, and 3 all go into 18. Again, you don't have to do it this way, but I just find it easier to do it this way. So you have 2 over 18 plus 3 over 18 plus 6 over 18. You add those up, you get 11 over 18 is equal to 1 over the equivalent resistance. Oops, let me move that down. But you don't want 1 over the equivalent resistance, right? You want to know what the equivalent resistance is itself. So let's find out then what 1 over, what the reciprocal would be. Req over 1 equals 18 over 11 then. So 18 divided by 11. Let's figure out what that is. Once we figure out what that is, then we're going to find what the equivalent is on our answer. 18 divided by 11, you get 1.6. Is that one of our options? Yeah, it is, right? Option number 1, 1.6 ohms. So Req is equal to 1.6 ohms. Okay, an object is thrown vertically upward with an initial velocity of 9.8 meters per second. What is the maximum height reached by the object? Okay, so let's write down what we know, right? Initial velocity, we know, is 9.8 meters per second. And if we're throwing this thing upward, right? Here I am, I'm throwing the object up. It goes up. We know that gravity is acting on it. So our acceleration is gravity pulling us down at a rate of negative 9.81 meters per second squared, right? That's a constant. Anytime something is moving in the air, you have an acceleration of negative 9.81 meters per second squared in the vertical dimension. So what else do we know? We want to find the height. So in other words, we want to know the distance it traveled. How high up did it go? What distance vertically did it go? Not only that, though, if we're talking about the maximum height, we know that at the point of maximum height, the velocity, or at least the vertical velocity, I'm going to write Vy, is 0. I only wrote Vy because we're specifically talking about the vertical. I mean, this one we're thrown vertically upwards anyway, so I didn't necessarily need to specify that because we don't have any horizontal velocity. But just remember, that's only the vertical velocity that's 0 at the top. So what we're going to say is that your final velocity, once you reach that point of maximum height, is 0. And then you're going to find a formula, same as we did in the last video, right? Find one that has all of these variables plus the thing that you don't know. So you have Vf squared equals Vi squared plus 2AD. Vf is 0 meters per second, and you square that. 0 squared is just 0, so don't really need to worry about that so much. 9.81 meters per second is Vi, and it's Vi squared, plus 2 times negative 9.81 meters per second squared times d. 2 times negative 9.8, that's negative 19.62 times d. And 9.8 squared, that one I can't do in my head, right? So let's see what 9.8 squared is. 9.81 times 9.81, you get 96.23. So 96.23 equals 0 squared, so that's just 0. We want to get d alone, so we're going to move that 96. So 96, we subtract over onto this side. And now we have negative 96.23 is equal to, oh, this should be a negative because it's 2 times negative. That's my fault. Negative 19.62 times d. We want to get d alone, so we divide by 19.62. And let's see what that is. 96.23 divided by 19.62. You get 4.9. 4.9 meters because it's a distance. So is that one of our options? Let's see. That would be option 2. There you go, 4.91 meters. Okay, this next one says, which type of photon has the least amount of energy? Well, if you're talking about the energy of a photon, right, E photon, you have h times f, Planck's constant, times the frequency, and hc over lambda. So what that means is that if you have a lower frequency, you have a lower energy. If you have a higher wavelength, you have a lower energy. So let's look at our energies for these types of, let's look at our frequencies and wavelengths for these types of light that they're giving us. We have ultraviolet, we have visible, we have infrared, and we have radio. So what you have to do is you have to look at your electromagnetic spectrum over here. Let me get this out of the way. And let's see ultraviolet, right? Ultraviolet you see is over on the, I don't know if you can see my mouse. Hopefully you can see my mouse, but it's over here. And you see that it has a frequency of about like 10 to the 17th power, 10 to the 16th power, 10 to the 15th power. Pretty high frequency. So remember, higher frequencies mean higher energies. We want a low frequency to have a low energy because they're asking us which one has the least amount of energy. So let's see the other ones. Well, visible light is right below ultraviolet. And then if you look even further, you have infrared, even lower frequency than visible light, right? 10 to the 13, 10 to the 12, you have infrared. And then our last one that we have radio waves. Radio waves are all the way down here, very low frequency, 10 to the 9th, 10 to the 8th power, 10 to the 7th power hertz. So in terms of the lowest energy, the lowest frequency would be our radio waves. So that's going to give us our lowest energy. Okay, so here in this one, we're looking at an inelastic collision where two objects come together, they stick together, and they move together, right? So for example, like these two pens. Maybe this pen right here, or this marker, excuse me, is stationary. This one comes along and hits it. And instead of them hitting each other and bouncing off of each other, it hits it, and then they move together. That's what's happening in this case. That's an inelastic collision. Right? Inelastic, think like they're not bouncing. Elastic, think they bounce. A 7.5 kilogram 7.5 kilogram object moving at 20 meters per second. So let's draw that out. We have, this is 7.5 kilograms, and it's moving at 20 meters per second. It strikes a 60 kilogram object, that's initially at rest. So if it's initially at rest, your initial velocity for that one is 0. It's on a frictionless horizontal surface, so we're not going to be losing any energy, either in potential or kinetic. The two objects stick together and move off at a speed of blank. So for this one, you have m1, well, really it comes down to this idea of the conservation of momentum. P before is equal to P after. The total momentum of them before is equal to the total momentum of them after. The inelastic formula you'll have to remember is m1v1 plus m2v2 is equal to their combined mass, because now they're moving as one object. So I say m1 plus 2 times now they're moving with one speed, so just v. Plug everything in, right? Mass 1 is 7.5 kilograms. Velocity 1 is 20 meters per second. Mass 2 is 60 kilograms. Velocity of 0 meters per second. They have a combined mass after of 67.5 kilograms. You just add their two masses. We want to find what v is, their combined velocity after. So this is just going to be 0, right? 60 times 0 is just 0. Let's figure out what 7.5 times 20 is. Let me do the math on that real quick. We have 7.5 times 20. You get 150. So you have 150 is equal to 67.5 times v. Right? And if we want to get v alone, we're going to have to divide away that 67.5. So let's go ahead and do that. 67.5, divide on both sides. 150 divided by 67.5. Let's see what that is. 150 divided by 67.5, and you get 2.2 meters per second is equal to v. Let's see, is that one of our options? Yeah, option 2, 2.2 meters per second. How is the electrostatic force between two positive charges affected as the charges are brought closer together? Well, let's look at our formula for this one. If we're talking about the electrostatic force, remember we do have a formula for the electrostatic force. Go to your page all about electricity, which, let's say right at the top, right? Electricity. Electrostatic force, you see, is Fe. We have a formula for Fe right here, K Q1 Q2 over R squared. Now, if we bring those two charges closer together, right, that value of R would be getting smaller. Let me draw it on the paper so I can show you what I mean. Oops. Here we go. Right, so we have the formula Fe is equal to K Q1 Q2 over R squared. And what they're saying in this question is that we're going to be bringing these two charges closer together. So we're decreasing the distance between them. R is the distance between them, which means we're going to make this value smaller. We want to decrease R. Well, if you decrease the value of R, you're now dividing by a smaller number. If you divide by a smaller number, you get a bigger result, right? You're going to get a bigger value for Fe. So the force of attraction or the force of repulsion then we're coming down to, right? Because we have two options. We know the force is going to increase if we bring them closer. The distance decreases, this increases. But are we going to have a force of attraction or a force of repulsion? Well, let's see. It says between two positive charges. So they're both positive. Remember, like charges repel each other. So we have a force of repulsion that's going to be increasing. So that would be, let's see, force of repulsion. Option 2, force of repulsion between them increases. What is one difference between magnetic forces and gravitational forces? Magnetic forces are always attractive. Nope, we could already eliminate that, right? We just said in the last question that magnetic forces can sometimes be repulsive if you have two like charges, positive and positive, repel. Magnetic forces are always repulsive. Again, number 2, nope. Magnetic forces may be attractive or repulsive. That's good, right? Because you could have positive and negative attract or positive and positive repel. So let's see the rest of that. Number 3, whereas gravitational forces are always attractive. Yes, right? Gravitational forces are always attractive. You're never going to be sitting and be pushed up to the ceiling, repelled by gravity. Gravity only pulls things in. It only attracts things. So that's option 3.